Okay, Assalamualaikum warahmatullahi wabarakatuh. Hello, Padai and everyone. My name is M. Jabar Alvensena. I'm from Numerical Method 1, and my student number is 1906-356-336. In this occasion, I would like to present my final project results called gas turbine optimization using multivariate Newton-Raphson method. This final project I conducted to finish the numerical method 1 class assignment. Okay, let's jump to our next slide. Okay, so outline of my study is that the first is an abstract, and then the second I will tell you about the introduction and then the objective, and the fourth is methodology, the fifth is results of my study, and then the sixth is my conclusion and the references I use in this study. So, wait a minute. Okay, so the abstract of my study is that, as we know, the numerical method is one of the methods that is often used in solving engineering problems. In engineering applications, numerical methods can solve various problems. For example, in terms of optimization. This article will discuss how the Newton-Raphson method helps us to optimize the output shaft power of a non-regenerative gas turbine cycle. The keyword in this study is that gas turbine optimization, numerical method, Newton-Raphson method. Okay, so the introduction. As we know, the field of thermal system design and analysis continues to develop, as well as the gas turbine system. This kind of open thermal system doesn't use the same air when it's done its cycle, are usually used in aircraft, trains, ships, electrical generator, and etc. Due to this tremendous area of use, we can find that so many researchers constantly developing this gas turbine cycle so that it can run more efficiently and more powerful. However, with the development of computing technology in the engineering field, we certainly can use the help of it to solve these various problems and equations by using the numerical method at ease. To be precise, this article will talk about how to optimize the gas turbine output power by using the help of Newton-Raphson method. To be precise, I'm using multivariate Newton-Raphson method because we need multiple equations and then multiple variables to solve. So, what is the objective of my study? In this study, I have two objectives to achieve. The first one is optimize. To obtain the optimal output power in kilowatt, the turbine can achieve at certain boundary conditions. And then the second is experience. To obtain real-life engineering experience use of the numerical method. Okay, so let's jump into the methodology of my study. Sorry, I will. Okay, the first is model description of my study. The model used in this article is a normal gas turbine that uses a non-regenerative Brayton cycle as shown in figure 1. So this turbine draws air and rejects the turbine exhaust or pressure at point 4. Here it is. To atmospheric pressure of 101 kilopascal. As we see here, it is 101 kilopascal. And the entering air temperature or temperature at point 1 is 25 degrees Celsius. The maximum energy added to the combustor by burning fuel or Q is 8,000 kilowatt. So, as we have studied earlier in the third semester, if you'll remember, in basic thermodynamics, we have already learned about Brayton cycle. So here I will flashback a little about how Brayton cycle works, especially non-regenerative Brayton cycle works. So the Brayton cycle uh, have three main component, and then one optional component. So the first one is compressor. It uses to raise the air pressure or the work fluid pressure uses in this turbine. And then the second one is combustor. The third one is turbine. and then the work from turbine will then transfer to our main power target, and then half some of the turbine output will then transfer to through a compressor to turn on the compressor. So the workflow is that the first, the air from the environment is taken into the compressor here in point one. As we see here, in our case, we take the air in environment at 25 degrees Celsius and at pressure 101 kilopascal, or at atmospheric pressure. So the compressor will then compress the air, then it will come out as pressure at point 2 or P2 and temperature at point 2, T2. After it then have enough high pressure from the compressor, then it will transfer to a combustion where the high pressure air and high temperature air will then given fuel or given heat. In this case, we give 8,000 kilowatt in the combustion, and then the compressed air will then explode, and that explosion will then transfer to the turbine, where in the turbine the exploding gas will then expand, and the expansion moves the the turbine, the the impeller of the turbine. So that movement of the turbine will then cause energy, and then we can transfer it to the main power target, that rotational energy. And then some of it will then transfer to a compressor through a shaft. As we see here, there's a shaft. So in this case, we will assume energy needed by compressor is as EC, or E compressor, energy of compressor. The input power is Q in kilowatt. Then the turbine we have ES, or E shaft, energy transferred to the shaft. And then ET is the energy transferred by turbine to the main power. Okay, so let me clear the annotate. Wait a minute. Okay, so there is a little flashback to our third semester learning about Brayton cycle. So let's jump to our next slide, where we have the assumptions. In solving this study, I'm using 4 assumptions. The first one is the gas or the air in this Brayton cycle is perfect gas properties throughout the cycle, and at CP is pressure constanta, is constant at 1.03 kilojoule per kilogram Kelvin. And then the second assumption is we are neglecting the mass added in the form of fuel in the combustion, so that the mass rate of flow, W, is constant throughout the cycle. And the third assumption is neglect pressure drop in the combustion, so that pressure at point 2 equals to pressure at point 3. And then the high pressure in the system can be designated simply as P. Okay, the last assumption is that neglect heat transfer to the environment. So to simplify it, we use these 4 assumptions to make it more easily to solve. Okay, let's jump to the mathematical model. So here, we have the compressor graphic, which inlet pressure of the compressor versus flow rate of the compressor. And then the right graph is the inlet pressure of the compressor, and then the turbine power we transfer to the turbine from the compressor. So here the performance characteristics of the axial flow compressors and the gas turbine operating at 120 rotation per second with an atmospheric pressure of 101 kilopascal that will be used in the study are shown in figure 2 and 3, respectively. this figure here we have is the figure 2, where it is a figure of axial flow compressors relation to the flow rate and turbine power. From this figure, we can develop the equations below. We can obtain the equations P equals to 331 plus 45.6 W minus 4.03 W to the W squared. We have the equation 1, and then we have the second equation where EC means power required by compressor in kilowatt, equals to 1020 minus 0.383 P pressure plus 0.00513 P to the square. We have the equation 2, where P equals to discharge pressure of the compressor in kilopascal, W is mass rate of flow in kilogram per second, and then EC, as I said earlier, it is a power required by compressor in kilowatt. So from this graphic, we can obtain these two equations from these two graphics. Let's jump to our next slide. Okay, the next mathematical model is in the previous slide we are studying about the compressor. The next is we have the graph of the turbine. So when operating at a given speed and discharge pressure, which speed is 120 rotation per second and the discharge pressure is 101 kilopascal, the characteristics of the turbine take the form shown in figure 3. This is a figure 3 where the turbine inlet pressure versus the turbine flow rate. Here we are, and variation of the temperature. We have 700 degrees Celsius, 807 degrees Celsius, and 900 degrees Celsius. And then on the right graph, we have the inlet pressure of the turbine versus the turbine power in temperature variation also. So from figure 3, we can also develop the equations below. Here we have the equations W, or mass rate of flow, as we know earlier. So we have this equation, this long equation, for sure, it is a multivariable. And then this equation 2, where ET is power delivered by turbine. So we have this long equations 2 also. It is a multivariable equations, where T equals to entering temperature, or T at point 3, T3 in degrees Celsius, and ET is power delivered by turbine in kilowatt. So, so far we have 4 equations. And then the next is to achieve these simulations, the values of the following unknown variables must be determined. We need W, P, energy by compressor, T at point 2, E energy transferred by shaft, and T3, and energy transferred by turbine. So we have these 7 variables, unknown variables. As we know, we also need at least seven independent equations that must be found to solve for this set of unknowns. So far, we have 4 equations, and then for those 4 equations is obtained from the 4 performance characteristics of the compressor and turbine. So the 3 other equations come from energy balances, if we remember in our in the basic thermodynamics class. So the energy balances, from the energy balances we can obtain 3 more equations. The first one is from the compressor. We are studying the compressor now. We have the equation as EC, energy transferred by compressor, equals to W, mass rate of flow, times pressure constant, or CP, times T2 minus 25 degrees Celsius. We have that equation 5. And then the 6th equation, we have we study the combustion now. The equation is 8,000 came from the fuel added, or Q, equals to mass rate of flow times constant pressure constant, or CP, times temperature at point 3 minus temperature at point 2. There we are, we have our sixth equation. And the last equation is we study the turbine power, where the equation is ET equals to EC plus ES, where ET is energy transferred by turbine, EC is energy transferred by compressor, and ES is power delivered to the shaft in kilowatt. And this is our seventh equation in total. So from this seven equation, we are next jump to the analysis method. So as for this study aiming to optimize the output power of a gas turbine, which required to solve multiple equations and multiple variables simultaneously, we can't use the univariate Newton-Raphson method because it only allows one variable at a time. As I say earlier, instead of using the univariate Newton-Raphson method, I find it that the multivariate Newton-Raphson method fits perfectly with our obstacle in this study. The multivariate Newton-Raphson method algorithm flowchart can be seen on figure 4 on this slide too. So the algorithm is simply like this. The first we have initialization, a first guess value. From that guess value, we are using Newton-Raphson method to calculate the result of f epsilon r. Epsilon r means the new x value from our first guess value. So we calculate the f of epsilon r, and then after that we calculate the 2 times 2 Jacobian matrix. After we calculate and get the results, we are continue to calculating epsilon r and find the f of epsilon r, and then we test it and see if it converges. If it's a yes, then it will end. If it's a no, then it will calculating the inverse of the Jacobian matrix called J times J minus 1 in quadrant. So after calculating the inverse, we calculating the J inverse 1, the J inverse times epsilon. Next, we calculate the epsilon r, and then we get the new epsilon r. We are using the Newton-Raphson method to calculate the epsilon r here again. After that, it will iterate, and then it will iterate more and more and looping until it is convergence at some point. And then when it's convergence, it will then end the iteration. So that's the method I'm using in this study. So from the back to our 7 equations, those 4 equations and those seven equations we are using is then input to the Python coding in multi-rate Newton-Raphson method. Then from the coding we can get the detail of these 7 values each iterations, and I input it in the Excel in form of table so that we can see it easily, more clearly. So in the mass flow rate variables, I'm using the trial value 10 kilogram per second. The pressure 300 kilopascal. Energy transferred by compressor I'm using 1000 kilowatt. The temperature at point 2 or temperature after the compressor is 250 degrees Celsius. The energy transferred to the shaft is 1500. And then the temperature at point 3 we have 800 degrees Celsius, and then energy transferred by turbine is 2400 kilowatt. After our first value, we then run the Python code, and then after the first iteration, we can see the values jump at least a little drastically from 10 to 10.91, 300 to 352, blah 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 blah, and so on, until at some point it is converge. I mean, as we see at iteration 3 and iteration 4, we see that the almost all of the variables don't change at all. Don't change drastically. I mean, it changed, but it changed just a little, very very little. So then this result we know that given the trial value needed for the 7 variables, using the multivariate Newton-Raphson method, we obtain that this mathematical model converge at 4th iterations. Lastly, we know that the optimum output power of the turbine, given the input power of 8,000 kilowatt, is this 1,598.5 kilowatt. So yeah, the object as I said earlier, that the objective of the study is that to find the optimum output power of the turbine. So we get here at the input power is 8,000 kilowatt. We get the optimum optimum output power of the turbine is 1,598.5 kilowatt. So yeah, let's continue. So I think the conclusions from this conducted study, we can conclude that the first is the optimum output power gas turbine can achieve at given 8,000 kilowatt as the input energy is 1,598.5 kilowatt. And then the second is we know that multivariate Newton-Raphson method can solve complicated multiple equations and multiple variables quickly. In this case, we achieve the convergence at 4th iterations. So yeah, maybe we can conclude that this method can solve complicated multiple equations and multiple variables quickly. So in conducting this study, reference I used is that the book Design and Optimization of Thermal Systems, second editions, written by Yogesh Yaluria in 2008, and Design of Thermal Systems, third edition, written by Wilbert F. Stoker at 1989. So that's all from me. For my final numerical method final project. If there is any critiques, any advice, or maybe you have some confusion about my explanation, you can don't be hesitant. Please to comment on the section below. So I want to revert a little about Padai says that think not of consciousness, use your heart to understand it. Last but not least, thank you and stay conscious. Assalamualaikum warahmatullahi wabarakatuh.